Welcome to AI Peer Review, your shortcut to staying informed on the absolute cutting edge of artificial intelligence. Today, we're doing a deep dive into a really interesting paper from Meta AI Research. It's titled DINOv3 Self-supervised Learning for Vision at Unprecedented Scale. The speed of progress in AI, especially computer vision, it's just been incredible. But there's always been this massive bottleneck, right? This huge, sometimes painful need for manually labeled data. I mean, think about it. Someone has to tell the AI what's in every image, sometimes down to the pixel level. Well, this paper we're looking at today introduces what they claim is a groundbreaking solution. Our mission here is really to unpack how Dino V3 aims to cut out that manual annotation step, letting models scale up to enormous data sets and architectures much more easily. We'll explore how just one algorithm can learn visual features from all sorts of data, regular photos, aerial shots, you name it, and what simple but really effective strategies make this possible. And for you, our technically savvy listener, we promise to go beyond just the what. We'll really dig into the how these core innovations are pushing the whole field forward.
That's exactly right. And DINOv3 is fundamentally built on self-supervised learning, or SSL. SSL is, well, it's kind of a game changer for training these big foundation models that everyone's talking about now. The ones that can generalize across tons of different tasks. The beauty of SSL is that it learns directly from the raw pixels, figuring out patterns on its own. It doesn't need all that human-curated metadata that other methods, like, say, CLEP, rely on. I mean, think of it like learning to ride a bike. You don't need someone explaining physics. You just sort of get on and figure out the balance from the experience itself, right? SSL leverages that inherent structure in the visual data.
So the model basically teaches itself. That's the core idea, isn't it? No more needing armies of people labeling images, which means potentially almost limitless training data.
Precisely. That scaling potential is just massive, especially for these large visual encoders. We already saw hints of this with its predecessor, DINOv2. DINOv2 got really impressive results, even in tricky areas like histopathology, analyzing medical tissue slides, where getting good labels is incredibly specialized and, frankly, expensive. And beyond just scaling, SSL models have some really nice properties. They tend to be more robust if the input images change a bit. They capture both the big picture, global features, and the fine-grained local details. Plus, they generate these rich embeddings that are super useful for understanding physical scenes, like 3D structure. They're kind of like generalist features. You can get strong performance on lots of different tasks without needing specific fine-tuning for each one. A single frozen backbone can often do the job for multiple things.
And that's really key for fields where you just don't have good labels, right? Like you mentioned medical imaging, but also things like remote sensing from satellites, maybe astronomy, or even particle physics data.
Exactly. Places where you have tons of data, but labeling it is just impractical or even impossible. The long-term dream here is building ever larger, more powerful models by just feeding them vast amounts of this unconstrained data. It's perfect for lifelong learning, too, with the web constantly generating more visual information. But despite that promise, actually getting SSL to work reliably at massive scale, well, it's been tricky. DynaV2 fixed some earlier stability problems, but pushing things even further brought out new challenges.
Yeah, I can imagine. It's never quite that simple, is it? What kinds of hurdles are we talking about? You said more data isn't always better.
You got it. First off, just figuring out how to collect useful data from huge unlabeled piles is non-trivial. Just grabbing everything might not be the smartest move. Second, standard ways of adjusting the learning rate during training, like a cosine schedule, usually need you to know the total training duration up front. With these potentially massive, ever-growing data sets, it's like trying to plan your marathon pace without knowing if it's 10 miles or 100 miles long. But here's the really fascinating bit. Something they call the dense feature degradation problem. It was known, but nobody had really solved it.
Dense feature degradation. Okay, that sounds important. What is that exactly?
So dense features are what you need for tasks that require understanding fine details across the image. Think semantic segmentation, where you label every pixel, or depth estimation. What they found was that, especially with large models, say over 300 million parameters, and during really long training runs, the quality of these dense features would actually start getting worse after the initial phase. Even if the model got better at overall image classification, its ability to handle those fine-grained tasks would degrade. That kind of limits the benefit of just scaling up.
Right, so you get diminishing returns, or worse, for certain crucial tasks. So DynaV3 set out to fix these things. What were their main goals?
Yeah, basically three key objectives. One, train a truly versatile foundational model for lots of tasks and domains. Two, specifically tackle those SSL shortcomings, especially that dense feature degradation problem. And 3, make it practical by releasing a whole family of models, different sizes, that people can actually use off the shelf.
Okay, let's dive into the how. How did they pull this off? Data seems like the first big piece. You mentioned just grabbing everything isn't the answer.
Exactly. They were very strategic about data preparation. They started with a huge pool, something like 17 billion images from public Instagram posts, which already have some level of platform moderation, which helps. But then they didn't just use it all raw. They curated it into 3 main parts.
Three distinct parts. What was the thinking there?
So one part, the biggest one with about 1.7 billion images, was built using clustering. They used DINOv3's own features to group similar images, trying to get a really balanced coverage of different visual concepts. Another part was retrieval-based. They picked specific seed datasets relevant to downstream tasks they cared about, and then found images in the big pool that were similar to those seeds, more targeted, you see. And the third part just included standard public datasets like ImageNet, mainly to help optimize performance on common benchmarks.
Ah, so it's a curated blend, balanced coverage, task relevance, and benchmark optimization. Clever. How did they mix these during training?
They used an intelligent sampling strategy. Most of the time, they'd pull a mixed batch from all the curated components except ImageNet. But about 10% of the time, they'd sample a batch purely from ImageNet 1K. They found this mix gave them the best of both worlds, performing well across a wider range of tasks than any single curation method alone, according to their ablation studies.
Makes sense. Quality and diversity over just raw quantity.
Okay, now the model itself, this unprecedented scale, how big are we talking?
We're talking big. They built a custom vision transformer variant with 6.7 billion parameters. Just to give you context, the largest DINOv3 model was around 1.1 billion, so this is a major step up. They really beefed up the internals, larger embedding dimensions, more attention heads, and they added some newer architectural components like different position embeddings to help it handle varying image resolutions and aspect ratios better.
Whoa, 6.7 billion parameters. That's massive. How on earth do you train that without hitting that optimization horizon problem you mentioned earlier? Right, that's a key part of their training recipe. Instead of a decaying learning rate that needs a defined endpoint, they used a constant learning rate, constant weight decay, and constant momentum for the feature model update for 1 million iterations after an initial warm-up phase. This basically lets them train for as long as performance keeps improving without needing to predefine the total training length. Very practical for these huge, potentially open-ended data sets. They used a big batch size, 4096 images spread across 256 GPUs, and employed a multi-crop strategy, feeding the model different views of each image.
Okay, a robust setup. And the learning objective. What signals did they use to actually teach the model?
It's a mix, a discriminative self-supervised approach. They combine an image-level objective, kind of like the original Dino, for global understanding. They also use a patch-level objective, borrowed from iBita, which involves reconstructing masked patches, helping with local details, plus a regularizer to keep features spread out within a batch. And crucially, they found that adding a simple layer normalization step specifically to the outputs for local and global crops made a real difference. It stabilized training and actually boosted performance on both classification and, importantly, dense tasks. Sometimes simple tricks have a big impact.
Okay, huge data set, massive model, a clever training strategy. But what about that nagging, dense feature degradation? This is where gram anchoring comes in, right? You said this was the real breakthrough.
Yes, exactly. This is arguably the core innovation of DINOv3 for dense tasks. Remember, global performance might keep going up, but dense performance could start dropping. That was the big unresolved problem, limiting scaling benefits for things like segmentation. They figured out this degradation was linked to inconsistencies at the patch level. Features for fine details were becoming kind of noisy and less distinct over long training.
So gram anchoring, it sounds technical. How does it actually fix that problem?
It's quite elegant, actually. It's a new objective designed specifically to regularize those patch features and keep them consistent, but crucially, without messing up the global performance the model learned. The key idea is to work with the gram matrix. Think of the gram matrix as capturing the relationships specifically, the dot products between all the different patch features within a single image. It represents the structure of similarities. What gram anchoring does is it pushes the student model's gram matrix to match the gram matrix from an earlier version of the teacher model specifically, a version from a point in training known to have good dense properties. The neat part is, the individual patch features can still change and adapt as long as the overall structure of their relationships stays consistent with that better earlier state. This preserves the fine-grained detail.
Huh. So it's not forcing the features to be identical to the past, but forcing the pattern of similarities between features to stay good. That's really clever. It's like ensuring the relative positions of puzzle pieces are correct, even if the pieces themselves get refined.
That's a great analogy. And they implement it as a sort of refinement step later in training. After the model has learned the basics, they found that even applying it late could help repair degraded local features. The target gram teacher itself gets updated periodically. Interestingly, adding this gram objective had a clear effect on the patch-level iBot loss, making it decrease faster, but it didn't really disrupt the global dino loss much. This suggests it's having that targeted effect on dense feature quality, just like they wanted.
And did it work? What were the performance benefits?
Oh yeah, the impact was almost immediate once they turned it on. They saw significant improvements on dense tasks like segmentation on 80/20K pretty quickly within the refinement phase. They also found a cool trick. Feeding higher resolution images into the gram teacher, then downsampling the features, allowed them to distill even better patch consistency into the student model. This gave them another noticeable boost on dense tasks. Visually, if you look at the feature correlation maps in the paper, the improvement in sharpness and locality with gram anchoring, especially the high-res version, is really striking.
Wow, okay, so they fixed a major bottleneck for scaling SSL. Once they have this powerful, well-trained 7B model, what's the post-training polish you mentioned?
Right. A couple of important steps. First is resolution scaling. The model was trained efficiently at a base resolution like 256 by 256, but real-world applications often need higher resolutions, right? 512 by 512 or even more. So they add an adaptation phase, maybe 10,000 more iterations, training on a mix of higher resolutions.
And I bet gram anchoring is still vital there.
Absolutely essential. Without it, performance on dense tasks would likely degrade again at those higher resolutions. With gram anchoring, they maintain quality and get good generalization across different input sizes. They show stable features visually up to 4K resolution, which is pretty impressive.
Okay, high-res adaptation. And then making that huge 7 billion parameter model practical for more people involves distillation, right? Shrinking it down.
Correct. They distill the knowledge from the giant 7B model into a whole family of models. This includes smaller vision transformer versions, VIT small, base, large, huge, and even different architectures like ConNext. They used the big 7B model as a fixed teacher, and they developed a really smart parallel distillation pipeline. It lets them train multiple different student models at the same time, all sharing the computationally expensive forward pass of the big teacher model across the GPUs.
That must speed things up enormously.
Hugely. It makes distillation much more efficient. And the results are great. The distilled models offer frontier-level performance, but need way less compute for inference. What's really remarkable is that their largest distilled student, a VITH+, with about 0.8 billion parameters, performs almost on par with the original 7B teacher, which is 8 times larger. That makes the power much more accessible.
That's fantastic. And they also connect it to language, text alignment.
Yeah, they align a text encoder with one of the DINOv3 models, the VITL, to give it zero shot, open vocabulary abilities, understanding arbitrary text descriptions. They train a text model from scratch to match image representations, keeping the DINOv3 vision part frozen. A key tweak they made was to combine both global CLS token and local pooled patch features for the alignment. This helps match text descriptions that refer to specific details within an image, not just the overall scene.
Okay, that covers a ton of innovation. So the bottom line, how does Dino V3 actually perform out there on real tasks? You mentioned dense features were exceptional.
Exceptionally good is right. If you look at visualizations of the dense feature maps, like in Figure 13 of the paper, they're just noticeably sharper, less noisy, and capture semantic meaning much more coherently compared to other top models like SIGLIP or even DINOv2.
Strong words. Did the benchmark numbers confirm that?
They really do. On standard dense tasks like semantic segmentation, on datasets like 80/20K cityscapes or depth estimation, NYU V2 KDI, using just a frozen DINOv3 backbone with a simple linear probe on top. It significantly surpasses previous self-supervised and even weakly supervised methods. For instance, on 80/20K segmentation, it outperformed a model distilled from SAM, which itself relies on massive supervision. That's a big deal. It also set new records on 3D correspondence estimation, matching key points between images, highlighting how good SSL has become for 3D understanding. And it's top tier for unsupervised object discovery, finding objects without labels, which is super valuable when annotations are scarce.
And you mentioned it's surprisingly good at video, even though it's an image model.
It's quite remarkable, honestly. It shows amazing temporal consistency when used for tracking objects in video segmentation, achieving state-of-the-art results on several challenging video benchmarks without any video-specific fine-tuning. Even for just classifying entire videos, it holds its own against specialized video models.
Okay, dense tasks are clearly a win. What about the global features? Things like standard image classification.
Still incredibly strong and versatile. For image classification, especially on tough, out-of-distribution datasets where the test images look different from training, DINOv3 significantly beats prior SSL models, and it achieves results comparable to the very best weakly supervised or even fully supervised models. They state this is the first time an SSL model has reached that level on classification benchmarks historically dominated by supervised methods. It also excels at fine-grained classification, distinguishing between similar categories, like bird species again, beating previous SSL work and being competitive with weakly supervised methods. And for instance, recognition, like matching specific landmarks or products, it achieved the strongest results by large margins.
So it's not just excelling in specialized evaluations, it sounds like it's a genuinely powerful general-purpose foundation model for building more complex systems.
Absolutely. That's a key takeaway. Its features are so robust that you can plug it into existing systems, keep the DINOv3 backbone frozen, and get state-of-the-art or near state-of-the-art results with minimal extra training. For object detection, using a lightweight detector head on frozen DINOv3 achieved top performance on COCO, using far fewer trainable parameters than competitors. Same story for semantic segmentation with a masked two-former head.
That frozen backbone capability is huge. It means less compute needed for downstream tasks, faster development.
Exactly. And it continues. They plug frozen DINOv3 into the Depth Anything v2 pipeline for monocular depth estimation and set new state-of-the-art results across multiple real-world datasets. It really inherits and improves upon DINOv2's strong sim-to-real transferability. Similarly, just swapping DINOv2 for DINOv3 and another 3D geometry pipeline led to clear gains across the board. It's just a very solid, versatile feature extractor.
This really sounds like a step change. Tell us more about the family of models they released.
Right. They provide a whole suite, different sizes of Vision Transformers ZITs and also convex CNX models, catering to different compute budgets. The VIT family consistently beats other open source models, especially on dense tasks, while staying competitive on global recognition. And even the smaller VIT models show really stable features across different resolutions, which is great.
And the convexes. It's interesting, they distilled from a transformer to a convnet. Does that work well?
Surprisingly well. These distilled convex models are very efficient, great for edge devices or situations with tight resources, and they significantly outperform standard supervised convex, especially on out-of-distribution classification and dense tasks. It really shows effective knowledge transfer is possible even between quite different architectures. And that text-aligned version, DINO.txt, also performs very well on zero-shot segmentation and retrieval tasks.
So this SSL recipe they developed, is it truly universal? Did they try it on completely different types of images?
They did, which really underscores the generality of their approach. They took the same DINOv3 pre-training recipe and applied it to a massive dataset of satellite images, almost 500 million of them. They just had to adapt the image normalization slightly for satellite data. And on downstream tasks specific to Earth observation, like estimating forest canopy height from satellite views, these DINOv3 models trained on satellite data achieved new state-of-the-art results.
Wow. So the core recipe works just as well in that domain. What about the original web-trained DINOv3 on satellite tasks?
That's maybe even more impressive. They found that both the satellite-trained DINOv3 and the original web-trained DINOv3, when used as frozen backbones with just RGB input, set new state-of-the-art results on a whole battery of Earth observation benchmarks, classification, segmentation, object detection. They often beat models that used extra spectral bands, more than just RGB, or required extensive fine-tuning specific to satellite data. It strongly suggests that these powerful general-purpose SSL features can sometimes match or even beat domain-specific approaches.
That's incredible versatility. But training these behemoths, it takes a lot of energy. The paper was quite open about the environmental costs, wasn't it?
Yes, and credit to them for the transparency. They reported that pre-training, a single DINOv3 7B model used about 47 megawatt-hours of power. They put that in perspective as of roughly equivalent to driving an average EV for 240,000 kilometers, or 150,000 miles. For the entire project, estimating around 9 million GPU hours, they calculated a footprint of about 2,600 tons of CO2 equivalent. Their comparison was that this is about half the emissions from all the return flights between Paris and New York on a typical day. And they're careful to note this estimate primarily covers the GPU electricity consumption, not things like cooling infrastructure, hardware manufacturing, or disposal.
That is a sobering number. While the transparency is definitely commendable, it really highlights that ongoing tension, doesn't it? How do we balance the incredible power and potential benefits of these models against their significant environmental footprint?
It's a critical question for the entire field. There's no easy answer. The capabilities these models unlock are profound, but the resource costs demand serious attention, pushing for more efficient training algorithms, better hardware, and maybe rethinking how often we need to train models of this scale from scratch.
Absolutely. So, wrapping up, DINOv3 really feels like a major leap in self-supervised learning. It tackles fundamental limitations, especially with that clever gram anchoring technique for fixing dense feature degradation. This ensures the models are robust and reliable across a wide range of tasks as you scale them up.
Definitely. This deep dive showed DINOv3 isn't just about setting new benchmark records, though it does that plenty. It also offers a genuinely versatile toolkit with models for different needs, proving SSL can learn incredibly powerful features from unlabeled data across diverse domains, natural images, medical, geospatial, and often using just the frozen backbone, I perform specialized fine-tuned models.
So here's a final thought for you, our listener, to chew on. Think beyond the usual computer vision applications. If models like DINOv3 can learn such rich general representations from vast, unlabeled datasets, what currently hidden patterns or insights could they uncover in scientific fields? Areas where data is everywhere, but labels are virtually non-existent. What new aha moments might be waiting for us when AI can perceive structures in data that we haven't even thought to look for yet?